Hey everybody, this is InstructaBeats, back again with our second video. This is Depth 2.0. We're going to just finish off the rest of the example problems. Again, wanted to make the first video a little shorter so that you could feel some closure finishing that video and then opening another one when you're ready for it. So, Depth 2.0. We talked about using generalizations, eliminating information that could be inferred, and using literal equations to infuse depth. So this is another example, but this time using magic squares. Now, if you're not familiar with what a magic square is a square made up of rows, columns, and diagonals, where all of the digits in a row or in a column or in a diagonal have the same exact sum. So in this case, in this magic square, I have 8 plus 3 plus 4, and 8 plus 3 plus 4 is 15. So my magic sum is 15. Every row, column, and diagonal must equal 15. Now in this magic square, I know the sum's 15, so I can figure out this middle number really easily. 3 plus 7 is 10, the middle one is 5. Then I can figure out my diagonals easily. 4, 5 is 9, plus 6 is 15. 8 and 5 make 13, plus 2 is 15. I can check my column here. 6 and 7 make 13, plus 2 is 15. And I can fill out the rest pretty easily. And in a lot of the enrichment resources I've seen, they have magic squares. But they give you the sum either by giving you all three numbers in a column, row, or diagonal, or they just state that the sum is, and then they give you a value, 15. And they may eliminate a number. It may look like a magic square like this, but if you know that the sum is 15, then 8 plus 4 is 12, this must be 3. It's not really that deep. So how can we make it deeper? With a magic square, you don't have to limit possibilities. Like, for instance, in this magic square, I might say you're limited to digits 1 through 9. You don't have to do that. And this magic square is still solvable with just 3 points of data by eliminating a number. So I'm using that first suggestion from our slides. What is depth? Remove information or data that can be inferred. And in this case, that's exactly what I'm doing. I'm eliminating this 3. Now, how can it be inferred? Well, I know that this 3, or this unknown square, this 8 and 4, use this unknown number for a sum. Who knows what the sum is? But I also know that this 7 here also uses this unknown number for a sum. And I have this middle number that's missing. So if I'm thinking about this 8 and this 4 plus something equals this 7 and this unknown plus something. So this 8 and this 4, which I know is 12, it must equal this 7 and this unknown. So what's the unknown number? The unknown number is 5. And so I'm able to infer. I'm missing information, but that doesn't matter because this 8 and this 4 and this 7 all share this square. This column and this row share this square. So I know then that this 8 and this 4, which is 12, must be equivalent to the 7 and this unknown number because the 8 and 4 and the 7 and the unknown share this square. And so I get 5 there. Now from here, it's a matter of just guessing and checking. I've already figured out one piece of information. I can guess 1. And then I can go through and see, well, would that work? 8 and 1 make 9 plus 4 is 13. I know 1, 5, and 7 is also 13. So let me look at this diagonal. 8 and 5 already make 13. That means this corner must be 0. 0 and 7, in order to make 13, this has to be 6. And then I realized really quickly, well, this 4 and this 5 make 9 and this 6 make 15. It doesn't work. So this number here can't be 1. So I know the middle square is 5. Let me guess 2. 8 and 2 make 10 plus 4 is 14. I know 2, 5, and 7 make 14 as well. So let me fill out the diagonals since I have those 2 digits already. 8 and 5 make 13 to make 14. This corner must be 1. 4 and 5 make 9 to make 14. This must be 5. Well, 1 and 7 make 8 plus 5 is 13. It doesn't work. So I need to move on with my guess and check. Is it 3? Well, let me check it out. 8 and 3 make 11 plus 1 is 15. I know 3, 5, and 7. Add that up, I get 15. In order to get this diagonal to 15, 8 and 5 make 13 plus 2 make 15. 4 and 5 make 9. So to get to 15, I need a 6 there. So let me check my column, see if it works. 6 and 7 make 13 plus 2 make 15. So far, so good. All I need to do then is add it up. 8, 1, 16, 15, that works. 4, 9, 2, 15, that works. 1, 5, 9, 15, that works. And this magic square is complete now. So just by eliminating information, you made students use deductive reasoning to deduce that this must be 5 because 8 and 4 and 5 and 7 share this square. So you deduce that this is 5, and then from there utilize guess and check, all because you just took out one piece of information. So those are magic squares. I'm going to have another video come out about magic squares in the future, showing you how to create magic squares, which information can you take away from it to make it more deep, how to make magic squares more complex, and so on. So the last example for depth. You can limit information, but you have to make sure you can solve it. And I've said that multiple times in this video. Here's an example. How much weight should be placed on the left side to balance this scale? So you have 1/16 of a pound and you have 3/4 of a pound. So this problem is not all that deep. All you have to do is convert 3/4 into 16ths, and that's 12/16. And so you just need 11/16 more, and your scale is balanced. Not very deep. And surprisingly, I believe this example or something similar can be found in some of the enrichment resources that I've used in the past. Now take a look at this problem. I'm limiting information that they can use, using only the unit weights 1, 1/2, 1/3, 1/4, 1/5, 1/6, 1/7, 1/8, or 1/9, 1/10, 1/16. Make this scale balanced, meaning left and right must be equivalent. 2 30-seconds, that's 1/16 of a pound, and 3/4 is 12/16. So I know I need 11/16 more, but if I go through all the possibilities, I'm never going to be able to make 11/16. So what can I do? So I used the first suggestion, limiting information. The third suggestion, using generalizations. Well, this is a balanced scale. I know in an equation or a balanced scale, if I add something to one side, I have to add the same amount to the left side. If I can't add 11/16 to this left side to make it balanced, maybe I can add something to the right side, and then that'll give me some flexibility to add different unit fractions to the left side to make it balanced. And so you can already see how deep this problem is getting. What if I added 1/16 to the right side? I would have a total of 13/16. I would then need 12/16 on this left side to make the scale balanced. And I can do that if I were to add 1/2. 1/2 is the same as 8/16. And 1/4, which is the same as 4/16. So 1/16 plus 8/16 plus 4/16 equals 13/16. And my scale is now balanced. Now I'm giving you answers, but just imagine students going through this, trying to convert to equivalent fractions, trying to see if maybe they can come up with 11/16, because that's all they need for this left side to make it balanced. And then they're going to soon realize that, well, 1/2, if I convert, is 8/16. 1/4, if I convert, is 4/16. I can never get an odd number like 11/16, or even a 5 and a 6/16. None of that ever comes out as an option. So then they need to utilize generalizations of what they can do with equations or balance scales in order to figure it out. So those are the two last examples for depth. I hope that made sense to you. Just a real quick recap. You can remove information or data that can be inferred, but just make sure the problem is still solvable. Take the extra minute just to see, I made it real deep, but can they solve it? And you're going to see kids, if they know it's solvable, they're going to be much more engaged in those problems because now they're curious. It's a mystery to them. Utilize literal equations when possible. Challenge students to find those values elsewhere. How cool is it that they can get on Google Maps and measure distance by right-clicking and selecting measure from this point to that point? It's a really fun tool to use, and you're eliminating information and forcing them to find those values elsewhere and utilize their understanding of volume or of area or of perimeter. And finally, force students to make those generalizations. Force them to understand, if I have 4 addends, but they're not regrouping, then those digits cannot be more than 2. If I have 3 addends and they're not regrouping, then those digits cannot be more than 3. Those generalizations can really help students tackle real life problems. Not just 1 plus 2 equals 3. So again, hopefully you've already subscribed, and if you haven't subscribed, please subscribe. We are at InstructaBeats Official. Our Instagram is at InstructaBeats. Be on the lookout for a Magic Squares video that's coming out in the future. And then we may talk, complexity video first is coming out in the future. And then a Magic Squares video. And my Mr. B, my second half of InstructaBeats, he'll be putting out student instructional videos constantly and so forth. So please be subscribed with notifications on so that when those come out, you can be one of the first ones to watch and challenge your students.